right? Whatever direction, right? You're dragging it through a charge field because there's a static electric field on Earth and there's a downward current. This linear a field goes up in voltage the higher you go, right? But it's a static field, right? And there's a slight downward current. Well, in this static field, um, at rest in a static field, a piezo-resistant material will read a constant resistance. But when you move it through the field, its resistance will change, and its resistance will change in proportion to the rate at which it's moved through the field. So the same way a piezoelectric works, just instead of the presence of the field, it's the motion through the field. And that will induce a resistance change and mechanical deformation.
On this principle that you're talking about right now, and I'm like, I was dying just listening to you talk about piezo. I can't even say correctly. Talking about right but now, basically like, pressure and how it creates electricity through the spark.
Yeah, bro. That was one of the technologies I referenced in my list. And as far as I can tell, I've looked at Merriam-Webster and I've looked at like other dictionaries and pronunciations. There's 3 different pronunciations for the word. There's piezo, there's piezo, and then there's piezo, right? But the word actually comes from Greek, and as far as I can tell, it's piezin in Greek. So I don't really care how to pronounce it. I pronounce it piezo. I pronounce it piezo. Sometimes I've probably pronounced it piezo. There's references to all 3, so it's kind of one of those like arbitrary pronunciations from what I can tell. But thank you for the correction.
Oh no, there was no correction. This was just strictly aligning with what you're saying, dude. No. Believe me, humbly, I'm approaching this subject. Truly, I appreciate you, my dude.
No worries, bro. Thank you so much. But as Toby was saying, in our like we looked into this particular device quite a bit, and getting 3, 4, 5 heads on it. It's curious because in theory, you should be able to design this entire setup, just have springs right there and have this mass here and have this little wafer here, but not make this out of silicon, not make this out of a piezo-resistant material. Just make it out of any kind of material as long as it has a constant resistance throughout the material, right? That way, this little wafer arm, the resistance along it will be constant. There won't be any resistance changes in it, right? And then you can make all kinds of materials like that, right? In fact, it would be a lot cheaper and easier, most likely, to make a material like that that's not piezo resistive. So the fact that they use it's weird, because if I was to put, uniform wood, uniform obsidian, and it was centered, it's going to read the same charge on the left and right. And if I move it, like all the readings should in theory be the same. So the fact that they use this material is very interesting, because as I was describing here, this piezo resistive effect, we know that in the presence of an electric field, just the presence of the electric field in proportion to the amount of current in the field or the charge of the field, the magnitude of the field, piezoelectric crystals will compress. But as I said, piezo resistive crystals, it's not the presence of the field itself that matters so much. It's the motion through the field, regardless of the magnitude of the field. Because just like moving, imagine putting a cell phone in a swimming pool of perfectly still water in the perfect center of that pool. Okay. It's got a constant amount of pressure on it at that time when it's just sitting still. The amount of pressure is not changing. But when you move that cell phone through the water, you're making it come in contact with more water. And if you make the water just like electrical charge, because a lot of people think of electricity in terms of similarity with water, then the faster you move it through the water, the faster it's coming in contact with more water. Just as the faster you move a piezo resistive crystal through Earth's static field, the faster it's coming in contact with more charge. And that motion, since you got a field that's static and a body that's moving, it's the same as if the body was static and the field was moving. It induces an electric current flow. And so the direction of that electric current flow through the piezo resistive crystal will induce a deformation along that same direction, proportional to the motion. Excuse me for one sec.
Yeah, I think you lost a few people, but I'm with you.
Dude, I can't wait for the pyramids part. Holy smokes.
So, anyways, does anybody need to ask any questions to clarify? We can do it after the slide. So the okay, okay. It crashed for both of you? Okay, wild. Anyways, so back to the motion through the static field. The faster you move this thing through a static field, this piezo resistive crystal structure, the more of a change of resistance you're going to encounter, as well as mechanical deformation. So we know that there are formulas, like Formula 5 here, for the amount of force that is applied to this system here, to this moving mass, um, when it's in motion. And you would think if it was purely a classical effect, right? If it was only, inertial forces that were at play, then the only forces that you would have in the net force equation would be on equation 5 here, Fm and Fk, right? You've got the force of the Proust mass and the force of the spring constant, but you have a damping effect here due to the damping material around the springs, and they will put oil around the springs. Most of the time, we found that the oil happens to be silicon oil, so that silicon oil is also piezo resistant. But equation 5 has a third variable, and it is Fb, which is the damping effect. So these springs have silicone oil around them, which dampens them because they fill this whole cavity up, this entire thing. They fill all the empty space in it, all the void space in the configuration that I'm talking about. And when they fill all the void space with silicone oil, there's no void space left. The oil is incompressible, um, at least to any kind of relevant magnitude of force on it, right? So when this thing moves in it, the spring becomes dampened by the oil. It basically buffers against the spring vibration force and helps to eliminate noise and things like that, making a clear reading. That way, that vibration isn't transferred into this rod, which is transferred into a vibration here in the capacitor field, which creates like a wobble on the graph. But also, it's interesting, and this is where we're not going to get to any like specific claims until further validation is able to be made. But at the very least, the one that we can make is that there's an FB, and we know that the FB is the force of the damping, but that damping would include any piezo resistive deformation that occurs, because deformation, since this is a free floating mass, should manifest, it seems, as motion, kinetic motion. Because if you try to deform this thing in a specific direction, but it's not against a solid surface like a wall so that it can actually squish and compress, then it's not going to be able to squish and compress against anything because it's going to be pushing against a spring. So it's just going to move this way or that way. But we don't really know the magnitude of that. It's just very interesting because they don't have a 2-variable force equation. They got a 3-variable force equation. And when you put these things in free fall, a profound implication of this equivalency is demonstrated when these devices are placed into free fall. In free fall, you can test it with your phone. I actually did it earlier today. A free fall induces a 0 acceleration reading on a MEMS accelerometer. That's because even though the entire device is accelerating downward, and then don't read the rest of that slide, even though the entire device is accelerating downward at 9.8 meters per second, there's an equal and opposite magnitude force applied upwards at 9.8 meters per second squared, so that there's a net 0 reading. But the weird thing is that sum is made of not just the force of the spring and the force of gravity, but by those two forces plus a third force, right? So that's the weird thing. Take from it what you will, what it might mean. We'll talk about it in a future presentation, hopefully. Moving on. These are just some proof slides for those who wonder about that. Yeah, that's the main claim. Yeah, so just to be clear about why it's curious, the main claim is that the damping material in there, right, is to eliminate noise and increase sensitivity and stuff.
Which makes sense.
Yeah, that part makes sense for sure because it's a fluid, an incompressible fluid around a spring, right? But the weird implication is that it seems like you cannot get away from the fact that, like, if you induce the piezo resistive effect, then you're going to encounter mechanical deformation, which manifests as mechanical motion, right, along a direction. So if you are moving this thing through Earth's charge field, there would seem to be a response, even if it's a very small one or a very big one. We can't say how big it would be. All we can really say is that it should be a non-zero response, because I don't think that it doesn't make sense to just turn this thing off like a switch and say, oh, it's not going to be piezo resistive in free fall, right? It's just not going to be doing that. Like it's always piezo resistive all the time. So it's just interesting that it's not spoken about, but it should be a force included in the force equation. So that's why it was brought up that if it was a thing, it would most likely be right here in FB. But anyways, moving on. Anybody that wants to know about the linear relationship, this is just a slide showing that, the linear relationship between acceleration and the relative change in resistance. Now we got more information, and I'm going to skip over this right now because it's, we talked about it. We don't need to go super deep into it until we get to the quantum part. But this is from basically the modern handbook on piezo resistive sensors, and it has large sections on accelerometers. So it just talks about how these acceleration sensors work. They're very small. They have linear relationships. You can use the flow through the material to induce resistance changes, or you can induce compression on it, and it'll do. You can induce flow through it, and it'll induce compression on it, and vice versa. So that's just what we talked about with the accelerometer. Right here, though, we get to this weird math, and this makes it even more interesting when you look at the way this stuff works. Because we know that these crystals are interacting with this mechanical motion, this electrical field, at a very, very tiny, like subatomic level or submolecular level at the atomic level, right? And so when they try to describe how it actually works, they start getting into quantum mechanics, energy band theory, Schrodinger equations. But they get to this point where they define the mass of the electrons as a negative amount. And, they would say that it's just a mathematical construct. It's just like a placeholder. It's just to make the equation balance out and work right. Sure, I get that. But, like, you're still describing something in the setup while these crystals are, in motion and stuff, as particles having a negative mass. And that doesn't really work in reality. You can't have, what would it be? Like antimatter or like a black hole, like a void black hole or something, So that doesn't really work unless they're saying that these crystals, as you're moving them around, they're generating antimatter or black holes inside of them, right? But if you think about it in terms of forces, if you look up here, force equals ma, right? Which is mass times acceleration. So if you have a force vector along an axis, let's say up and down, and you have forces moving down and you're representing down as the positive direction, then if you wanted to represent a force in the opposite direction, what would you do? Well, you would just give it a negative acceleration or a negative mass, right? And that would invert the direction along the vector of the force. So if there was a drag, not saying that there is, can't say for sure it's happening, but if there was a drag on these crystals as they're moving through the Earth's charge field, and and that's inducing a force like mechanical motion in the opposite direction, you would use math that would represent it as a negative mass because it would result in negative force. So anyways, either way, it's still interesting that they describe it as quantum, because the more you look at quantum mechanics and you research ether theory, the more parallels you discover. For those who are more familiar with the ether theory and the ether mechanics, you probably already know about a lot of these parallels between those and quantum mechanics. But for those who don't know, quantum seems to have attempted to hijack a lot of things about the ether, and hold on, let me change my window.
Yeah, compression is charge, right?
Yeah, word. So the magnetostrictive effect. So just like you have piezoelectric crystals, there's also piezomagnetic crystals, but they don't call them piezomagnetic. They call them magnetostrictive. But the magnetostrictive effect is the mechanical deformation of a material in response to the induction of not an electric, but a magnetic field. And the converse or inverse magnetostrictive effect, they call that the Villari effect, which is the induction of a magnetic field, or increase in the magnitude of magnetic properties in response to mechanical stress or strain. So an easy way to think of materials that exhibit these effects is to think of them as the magnetic version of a piezoelectric material. Now, when it comes to magnetostrictive materials, there's a much wider array of behavior that they exhibit, because some of them exhibit high linearity in the proportionality, whereas some don't. Some exhibit hysteresis, which is just one way versus the other way is not the same magnitude. But the ones that do express a high linearity, they're very useful because they can be used to design very highly sensitive sensors, like force sensors, but ones that have a very large effective range, right? So these materials can endure a lot more mechanical stress or strain than things like silicon can or quartz can. So they can be used to measure very, very large ranges of forces. One of the most foremost crystalline structures that's engineered for this purpose is an alloy known as terphenol D. They make it of 3 elements, iron, and then they blend the iron with terbium and dysprosium. Usually it's almost 1/3 each ratio, 32, 32, 36.
The fuck is terbium and dysprosium?
Right, those are like some rare earth elements. It
Super
seems
rare
like.
earth. Yeah.
Yeah, they're doping this iron with the rare earth metals and making it, go backwards compatible linearly on on magnetism and compression. The profound, like the technological implications of this are super interesting. I'll get to those after this, but this is just an article showing output characteristics and experimental study of a highly linear and large range force sensor based on the Villari effect. So that you can, this is just to prove the linearity that's possible with this effect too, just like piezoelectricity. They make these giant magnetostrictive materials right here on the left, like terphenol D. Really big coefficients on their magnetostriction. But it says in this study, the characteristics of terphenol D, such as its high compressive strength and fast response speed, were combined with the research experience of previous scholars to design a terphenol D-based force sensor with high linearity and a large range. The magnetic field uniformity of the model was verified using COMSOL simulation software. So it talks about how it's very linear, and then it makes improvements over previous technology that didn't work as well. And it says this model describes the process, and the validity of the mathematical model was verified by comparing the experimental and numerical results. This provided a technical approach to the in-depth study and accurate control of this giant magnetostrictive force sensor. So they successfully made ones that were actually useful and could be used to measure these things with linear relationships. Terphenol D is patented apparently. So and apparently the production mechanisms to produce it are I guess proprietary in a lot of ways. But I guess you'd want it to be, right, if you engineered this awesome substance that can make these super useful sensors. But something that's an implication of this in terms of technology, if you think about the magnetostrictive effect, if you were to take a block of that material and you were to squeeze it, it would generate a magnetic field. Okay, so it's an analog converter between mechanical and magnetic, just like piezoelectric's an analog converter between mechanical and electric. You could put these things together and put like one bar across the backs of them and press it, uniformly. You could generate an electromagnetic field, both of them together. When you cross section an electric field with a magnetic field, you create an electromagnetic field, which is EMF, which is visible light, all the bands of RF frequencies, right? So you can make light with it, you can make internet with it. And the thing about it is it's very interesting is it would be analog. So this would not be a digital internet signal that you're producing. It would be an analog internet signal. And since the inception of the internet, right, the internet has specifically been a digital technology. One of the main advantages, there are different advantages between both analog and digital. But one of the advantages of analog is that it's a continuous wave function, right? Instead of a discrete wave function like digital describes. So like digital's not a perfect curve because even the curve that they're building is made up of a bunch of points. And so, there's not that perfect curve, whereas analog is a true continuous function. So it can actually have theoretically infinite information density. There are functions that describe the relationship between the information density and other variables like distance and noise and interference and things like that. But the point is you could very greatly increase the bandwidth and throughput of the signal if it is analog. And when you talk about your internet speeds, that's your bandwidth, that's your throughput, right? We've got like certain internet speeds. There's fiber out now for people, so people are getting like 1 to 5 gigabit speed on their internet. And then the huge fiber pipes where they get like huge tunnel, like pipelines the size of like giant, tunnels, and just it's filled full of fiber cables that run into the oceans. Those have their own bandwidth too. But this, if you were able to perfect this technology, and there's actually research into this, right? There's research going on for this analog broadband technology. Then in theory, you could achieve like blinding internet speeds. So all this cutting edge research is just getting more advanced ever since the early 1900s, and we're getting to the point like we might be not breaking in a metaphorical sense, breaking the sound barrier on our internet speeds here soon in the near future. The last type of crystal I have on here is photonic crystals. These are crystals that have a unique property where they can, it seems, compress light. In layman's terms, at what it seems to amount to, because if you look at the waveforms, they get squished. But photonic crystals are specific crystal structures that have an emergent property concerning the filtering of certain wavelengths of light. Photonic crystals have band gaps that effectively compress or squeeze the light within that frequency range, causing interaction in a manner that's analogous to the way regular crystal lattices affect the propagation of electrons in a semiconductor, like silicon. So it's like instead of with electricity, it's with light, right? The band gaps present in the crystals prevent the passage of certain frequencies of light, leading to unique optical properties. Photonic crystals are often used in optics and photonics for controlling the flow of light in devices like lasers, sensors, and communication systems. The most well-known example of a natural photonic crystal structure is a gemstone known as opal. So if you want to think of, you had moissanite, you had quartz. With this, you've got opal. Cutting-edge research regarding photonic crystals have produced a wealth of profound findings, including the ability to perform parametric amplification of input signals, which is purported to result in a net gain compared to loss of this input signal. Other effects, such as superluminal speeds, have also been observed. So you've got like a net gain of magnitude on signal amplification, and you've got exceeding the speed of light, c, with these crystals. And so there's some examples of both of those. Talking about here the light speed, long-range superluminal pulse propagation in a coaxial photonic crystal, Hache and Poirier, 2001. This talks about how they were able to use these photonic coaxial cables in order to cause these light pulses to reach the other side of a 100-foot cable. Right. Actually, I think it was a 100-meter cable. And get there 3 to 3.5 times faster than they should be under the theoretical limit c, as defined by special relativity. So, we've got this breaking the light barrier breaking the Einstein barrier on light. And they have all kinds of explanations right here as to why it doesn't violate relativity. But it says right here from the paper, group velocity, which is defined as the traveling speed of the peak or center of gravity of the pulse, can indeed exceed c or become negative. However, since the transmitted energy is at all times smaller than that of an equivalent pulse traveling through free space, no useful information can be sent at superluminal speed. So what actually happens, what they're saying is the data signal, like we're going to send a packet, right? Like a file, whatever. We're going to send something. We're going to send data. The entire waveform, when it goes through this band gap, let's say it's an 8 to 12 megahertz band gap, right? Or 8.5 to 11.5, as we see in this image.
Right.
Then in between those frequencies, you're going to experience these shifts in these properties. And so they're saying that we see this waveform get squished and go a lot faster. It's getting squished and going super fast. It's almost like taking a garden hose, if you imagine the light as water, and you like squish the garden hose and like squish the nozzle at the end, right? And the water shoots out, right? You know, that's how you make a water gun with a garden hose. So this right here is doing the same thing with the light, except because the waveform is getting squished, it's distorting the waveform and messing up the data signal.
Right.
So they're saying,
yeah.
Right. So they are saying because the data signal's messed up, it's not actually sending anything. It's like, but like, bro, you're detecting it, right? You're not detecting nothing. You're detecting something. Let's say that like one light second, like because the cable's not that long, but to make it proportional, so for the understanding of the group, if you were to make the length of this cable 1 light second, so that in one in 1 second, based on the rate of c being the speed of light as a constant, the light would travel that far in 1 second. So we do the test and we power it on, and bam! Oh wait, it didn't get there, and that pulse didn't get there in 1 second. That pulse just got there in 0.3 seconds, 0.35 seconds, right? Like, what's going on? So they say, well, the data's messed up, so it doesn't break the rules.
Yeah. So, just to clarify on this, you're right. It's 100 meters, and this is like in this paper they're saying, anomalous dispersion is known to allow group velocities for electromagnetic waves that exceed c, the speed of light in free space. Such superluminal effects have been demonstrated in a number of optical experiments involving a tunneling of wave packets through resonant media and optical barriers. Recently, special types of interfering bezel beams were found to propagate at speeds slightly greater than c. So yeah, it's been like, it's not like this is I don't know. This has been repeatedly demonstrated, and it's known in like known science. So I just wanted to throw that in there.
Yeah, thanks for that, Toby, for sure, bro. Great addition. Yeah, they knew about this a long time ago. I think it was the 60s or 70s, right, when they first discovered it. But it wasn't as like great in magnitude back then. They were getting like 1.2, 1.4, stuff like that, like slightly above C. Like, we'll just write that off and say it's, well, But now, I mean, now they're like 3.5 C, right? With stuff like this newer technology. And that's just, you just can't do that, right? Like, they have to say all these special cases so that it doesn't violate their rules. But the fact is, you detected something. Like, the source of causation cannot be greater than C, right? If that's light, right? If that's whatever you want to call the thing that's traveling through here. If it's light or if it's something, unique and undiscovered that's faster than light that we don't know about. If you want to even say it's not light, whatever's traveling through here is going faster than C. Like, that's a fact because we turn on the device and it reaches one side to the other 3.5 times faster than it should be able to. So whatever it is, doesn't matter what kind of light wave it is, what kind of frequency it is, if it's squished or if it's not light itself, if it's something unique, it is moving faster than C. So they do all that, and you can't do. The beautiful thing about this is because the magnitude of this is so great, right? And it's not just slightly above 1. You can't really use length contraction and relativity to account for this. because what you'd be saying is that 100-meter cable, if it's like 3 point something X, would be undergo a length contraction, so it was shrinking from a 100-meter cable to a 30-meter cable while the experiment's being conducted. And
Yep.
nobody in their right mind is going to believe that, right? So I've got eyeballs, bro. I didn't see this, 3 football fields turn into a 1 football field, right? Like, get out of here. So that is a very awesome way that these crystals can be used. And the other thing that they can be used for that's very interesting is this parametric amplification. So they can use these crystals, and they specifically look for crystals that have a non-linearity. They try to get it as like non-linear as possible, I suppose. But they make these, and they turn on a pump, which is a power source for everything to run, right? And then they input the signal, which is like a light or a laser beam or something, into the crystal. And it's a parametric amplifier, so it's like a crystal structure that's been like custom made in a lab and doped and had all this stuff done to it. But it's still, some combination of elements. And they're actually able to take these photonic elements and induce a net gain in the signal compared to loss across its propagation. So you can imagine the usefulness of this in amplifier technology. And it says this fundamental absorption loss of stoichiometric, so I think it's silicon nitride is what it's called, waveguides was measured as low as 0.15 decibels per meter, which would facilitate parametric gain above 70 decibels, according to our simulations, using as little as 500 milliwatts of optical pump power, exceeding the performance of the best fiber-based parametric amplifiers. So, like, even if they go to like fiber optic technology that's like top of the line, they're getting way better performance out of this than they are even with that. So, like, this crystal research is enabling us to do crazy things. Go ahead.
What is a parametric amplifier?
So the parametric nature of it basically alludes to the nonlinearity and the response of the effects. But if you read over here on the left, they basically can get a continuous parametric gain. This is so the fact that it's continuous, right? What that means in the pulse laser propagation of the photonic crystals here in this first experiment, this was just pulse lasers, right? It wasn't a continuous laser beam. But this is using continuous light, which this even has cross implications with this, because it might indicate that you could do this not only with pulses of light, little dots of light, but continuous beams of light.
Right, but like, what is, like, for example, a fiber-based parametric amplifier? Like, what the fuck is that? Like, is that saying that you could use some type of fiber-based amplifier to repeat the signal farther? Like, I've never even heard of a fiber-based parametric amplifier, so I'm just curious if you knew. If not, it's cool. I'll look it up.
No, the reference 49 here is in the paper. I can link the paper and drop it in here.
Yeah. No
and there's this paper too, if you want that. But I as far as I can tell, the parametric is due to some like nonlinearity in the math. I could be wrong about that. That was my understanding. But there is a reference. In fact, if you want, I can just insert it here after this part, and we can look at it later. Take away the materials that like these of certain crystal elements, and then like mixing them together in a lab. They're able to do things like build computers, harvest electricity. They can filter EMF. They can improve our lives, improve our health. Even, well, don't read that line right there. But this type of knowledge was once seen as almost mystical by the ancients, who were aware of many of these concepts, though their technology was vastly different from our own. We may indeed see a future in which this technology is harnessed for the large-scale production, or rather collection and distribution, of energy for the benefit of all of mankind, right? But that's only going to be if, the people in charge, the powers that be, don't keep suppressing it and, try to keep their own pockets lined and pursue their own financial interests by shutting it down for us. But yeah, Alan's got his presentation after me. So, this is the segue right here. He's talking about the Sagnac effect. So this is just a screenshot of some modern technology that works off of that. That's can be used for such things as laser speedometers. So, and I'm sure he can talk to you all about kind of stuff like that. And I'll let him do it. I don't want to steal his thunder on anything, but that's my presentation.
Woo! Good shit, Piezo.
Yeehaw.
Dude, thanks, bro.
That was way longer than I intended it to be. My bad, bro.
No, that's straight. Straight. You never know till you do your first run through.
You got a lot out in a short amount of time. I loved it.
Thanks, bro. And you
Get
guys know a
yourself
little
a
bit more
Halls, bro.
Yeah, I've got oregano oil and what's that freaking herb called? Echinacea.
Nice.
Show.
But yeah, now y'all know more about crystals and how everything that we use today is powered by crystal technology. Kind of wild to think about, right? And a lot of these crystals are gemstones and precious stones. So it's super weird, bro, like that there would be a correlation between those things.
Yeah, thanks for putting the time in.
Yeah,
that was cool.
No worries, bro.
So yeah, Alan, whenever you're ready. So yeah, we're having, I don't know if it's like a regional thing or what. Alan's internet was being weird earlier. My internet, the stream seems to be good now, or but like it has been disconnecting and reconnecting like throughout the whole thing, to the point where we're gonna cancel like the rest of it and try and do it later. But we're gonna go through, and Alan's just gonna record on his end, so he'll get a clean recording. And I don't know, the stream is up, and it was working for most of it, but there's gonna be a few random like chops in there because it's just kind of choppy internet tonight for some reason. It's weird that Alan had a problem, man. We're both kind of in the Midwest, so it could be something regional here. But in any case, thanks again, Piezo. And Alan, whenever you're ready, go ahead and kick it off.
All right, yeah. All right, I got it set up. Is everyone transitioned or ready to go? Yeah, I guess we're ready. All right, cool. All right, so this is the Sagnac effect, and with respect to what is motion being measured against, right? So we're going to get into the full history of it. We're going to get into some the experiments that followed Sagnac, and try and figure out what's going on here. Okay, well that's not right. One second. Where's the rest of my slide? Okay, one second. Hold on.
Oh, good.
I just got to pull up this PDF real quick.
I saw that sneaky little Einstein quote.
Yeah, I don't know why Einstein's hiding. 1905. Okay.
I mean, to be fair, it's like you could really just have the whole presentation be that.
Yeah, dude, I know, right?
Good,
I was tempted
good game.
to just...
Thanks for playing.
Dude, it was super tempting to just do like 4 slides. All right, so this is from Einstein's 1905 paper on the electrodynamics of moving bodies. So this was following the experiments of Michelson-Morley.
We don't see anything in the Discord.
Oh, right. 1 second. Thank you, sir.
No problem.
All right, there's the new one. All right, so this is his 1905 paper on the electrodynamics of moving bodies. From the mathematics and framework presented in here, and the philosophy put forward here, is what redefined all of physics and enabled them to explain the Michelson-Morley experiment without showing that proportional velocity relationship in the fringe pattern, which we'll get to later on. But here we're just going to look at the basic premise of what Einstein is putting forward. And we'll go over the importance of why he's stating this. So he says here, examples of this short, together with unsuccessful attempts to discover the motion of the Earth relatively to the light medium, suggest that the phenomenon of electrodynamics as well as mechanics possesses no properties corresponding to the ideas of absolute rest. They suggest rather that as already shown in the first order of small quantities, the laws of electrodynamics and optics will be valid in all frames for which the equations for mechanics hold good. We raise this conjecture. The purport of hereafter will be called the principle of relativity to the status of a postulate. We will also introduce another postulate, which is only apparently irreconcilable with the former, namely that light is always propagated in empty space with a definite velocity of c, which is independent of the state of motion of the emitting body. These two postulates are sufficient for attaining a simple and consistent theory of electrodynamics of moving bodies based on Maxwell's theory of stationary bodies. The introduction of a luminiferous ether will prove to be superfluous in so much as the view here will be developed not to require an absolute stationary space provided with no special properties, nor assign a velocity vector to a point of which empty space an electromagnetic process takes place. So he puts his first two postulates down. We've got very specific parameters and conditions here. So the whole purpose of this theory is to explain phenomenon without invoking absolute space. So to invoke like a hypothetical distance change to preserve distance, or without assigning a velocity vector for electromagnetic propagation. So in regards to that, what that would be, if you were going to change the distance, if you were going to preserve a distance with absolute space, you would also have to change time. So like the time of propagation. So this would be in relation to that. So you would be preserving both points to explain a phenomenon. So Einstein's saying, hey man, we're gonna Lorentz transform our way out of this, and we don't need no absolute space, and we don't need to assign velocity vectors to an empty point of space in which electromagnetic propagation took place once, right?
Well, so
there's
then
our base.
When they go to explain something like Michelson-Gale-Pearson, isn't that exactly what they do?
Dude, first thing they do is that, and then right off the back of that, they say this is in accordance with relativity theory. It's the literal opposite. So I'm so glad you pointed that out, because yeah, we're gonna go through all of these contradictions. So shout out to this slide. I don't know what happened here, but that was supposed to be the introduction there to the theory. So let's see. Now, another important thing to note here in this in the 1905 paper is how Einstein defines an inertial frame. So as we were reading earlier about a frame in which the equations of Maxwell's hold true and whatnot, right? So what does that mean exactly? Well, if you're accelerating, if you're moving, are you still inertial? What are the rules, Ein? Tell us how it works. So Einstein says, if you are in constant uniform rotation, then you are in an inertial frame. And the logic behind that is, if you take any part of that loop and you extend it to infinity, it will not deviate from, or it'll like barely deviate from a linear path. Like it'll be just as good. So the logic behind it is like sound, as well established. It tracks, right? So this is Einstein incorporating that into his theories to explain a uniformly rotating device, which will become super important later on. So it is apparent that the results, so this is quoting Einstein from his paper, and I have two sources here. One's from another translation, like earlier, like from the 30s, I think, and then this one's like a more modern one. But anyway, it says here, so if we assume that the result proved for any polygonal line is also valid for a continuously curved line, we will arrive at this result. If one of two synchronous clocks at A is moved in a closed curve with constant velocity until it makes a return to A, the journey lasts t seconds, and then by the clock which has remained at the rest traveled on its arrival at A will be 1/2 t times v squared over c squared seconds slow. So that's the coefficient for time dilation, how much it's going to be slowed on its return trip. So based on its velocity. Thence we conclude that the balance clock at the equator, and he makes a special reference here that he's not talking about a pendulum, he's talking about a light clock. So essentially an atomic clock. So he wrote this before atomic clocks, obviously, but this is one-to-one analogous to an atomic clock. So a balance clock at the equator will move more slowly by a very small amount precisely to the clock situated at one of the poles, right? So that's his. So the important thing to note there is that when you're in uniform rotation, the equations still hold true, so it's still an inertial frame. So his theory still applies. So the rules of special relativity about the first postulates, where all inertial frames are equally valid, right? And the speed of light is constant. It's constant and independent of the motion of the source or observer, right? So in an inertial frame, right? So that's super important here, because we're going to go over multiple instances of inertial frames where the speed of light is different. So starting off here, we have Sagnac. In 1913, he used a uniformly rotating platform in optical media to photograph a fringe shift pattern. Now, his prediction for that, he mathematically derived basically that there would be an equivalence between the length that light has to travel and the air, so the area of the device and the rotational speed, the angular velocity of the device, would produce a directly proportional variance in the speed of light that would result in a fringe shift pattern. So if you have a disk and you split a light beam and it goes counterclockwise and clockwise and it completes its circuit, when it completes that circuit, there should be a fringe shift pattern that is proportional to that rotation. So after Sagnac, and we'll watch some videos on that so you guys can get some visuals on that and get familiar with it. But to summarize what Sagnac, and he made those measurements, he got the proportional relationship with his prediction. So he gives a summary here, a description of what he as how he's interpreting the results here. So he says, optical rotation effect. Measured from the fringe spacing, the displacement z and the interference centered at that I observed with the preceding method is a particular case of the optical rotation that the path that I have defined earlier. So he's talking about some earlier experiments he did and how he derived the equations. And with the context of the current ideas, we shall construct a direct observation of the luminiferous ether. In a system moving as a whole relative to the ether, the propagation time between any 2 points of the system should change in any way similar to a stationary system subjected to an ether wind, the relative speed of which at each point of the system will be the same and directly opposite to the speed of any point in which would contain the light waves, in a manner similar to an atmospheric wind carrying sound waves. The observation of the optical effect of such an ether wind relative to a quote-unquote stationary ether will constitute proof of the ether's existence, just as the observation of a wind relative to the atmosphere on the speed of sound in a moving system will constitute everything being equal with a proof of the existence of a stationary atmosphere enveloping a moving system. So remember, he's coming at it from the heliocentric paradigm, where his interpretation of that analogy is that the Earth is rotating and the atmosphere is moving uniformly with it. And within that uniform motion, there's wind that's going in, various directions, right? So that's what he's saying, is that he's equating it in that stationary regard. Now, the way that we're interpreting it is that the Earth is stationary. The atmospheric wind, the stationary atmosphere that's moving with the Earth is just moving, right? And like that's so it's just a moving ether wind, and then within that, motion whatever is moving, produces its own ether vortex, so that light or electromagnetic propagation is proportional to their velocity within that overarching ether wind. Any questions, comments so far?
Could you repeat what you said just like 2 seconds ago about instead of the heliocentric paradigm, we're interpreting it as?
Yeah. So the way I interpret it, right? Stationary Earth. You could look at a Gleason's map just for like a rough outline of what it would be like, and then there would be a vortex emanating from the center, and that rotation would substitute for a uniformly rotating atmosphere with the rotating Earth. And then motion within that vortex will have its own vortex proportional to its motion.
Gotcha.
So the only thing that changes here is that the Earth is stationary.
Right.
Okay, and then so now we're gonna watch a single axis gyroscope correction. So we're gonna look at a kind of classic setup, and we're gonna look at how they because Sagnac even proposed this too for measuring Earth rotation, and then they went and did it in 1925 or whatever. So this is, obviously Æther wind rotation, but we're just going through the paradigm and the history. All right, so we'll play this. This is by what's his name? Doug. Can't think of his last name. But anyway, his YouTube channel will be provided in the thing. So we'll watch this now. How do I make it full screen? Is that possible? All right. Well,
play it when it's full screen.
Plan B.
Can you double click it?
Yeah. There we go. I have to share it anyway with audio, so I'm just going to pull up the video. Okay, we should be good. All right, I'm going to play this at 1.5 speed and maybe 2 or maybe 1.5.
God damn it.
And then we should be good. Rest in peace.
There's no sound coming through if there is supposed to be. Oh wait, never mind.
I got sound.
I got sound. Yep.
You're good.
Sagnac interferometer that I'm going to describe today is the most sensitive one that I've built to date. What's different about this one as compared to the others is that we've gone to a much longer Sagnac loop. This time we've got a 1 kilometer single mode fiber as the loop, and other parts of it are very similar to the previous design. 2x2 coupler with 50-50 light going through each side, and with a polarization controller loop connected on one side of the fiber optic cable, and we're also using an amplifier after the detector.
Yeah,
this time we're using a
that?
common mode rejection amplifier, which
Cool. Quick side note. This is a 13-year-old video. There's only audio. It's mono audio or whatever, and it's super low. So.
Oh yeah, I'm only hearing that out of
Take it
one
off
speaker.
one.
Okay,
Yeah,
makes
yeah.
sense now.
Take
Yeah,
that to 1.0.
What's that? Yeah.
Take the speed off 1.25. Take it down to 1.0 again. Let's hear it again, man.
Yeah. Okay.
Thank you, Stone. That's right.
Fuck.
Suffer.
from the internal to the laser, and the other one is at the end of the 2x2 coupler, which receives the signals coming back from the loop. And we put each of these diodes connected to either arm of the common mode inputs, the idea being that they will cancel out some of the common mode noise between the two, and also will help control for intensity drift on the laser. So this amplifier gives a total amplification of between about 500 times and 1150 times depending upon the gain, and it also allows us to zero the signal by balancing the voltages between the two diodes. The fully assembled electro-optic interface is shown in this figure here. This is the completed Sagnac interferometer. It is on an equatorial mount so that it can be positioned in any direction horizontally or vertically with respect to the rotating Earth. For our Sagnac interferometer to experience the full rotation of the Earth, we have to align it so that its z-axis is parallel to the North Pole. Once it's in this alignment, which is shown in the figure here, it experiences the full rotation of the Earth at 1 revolution per day. If, however, we turn the device perpendicular to the axis of the pole as shown here, it will experience no rotation at all. In this next graphic of the Earth, you can see the two orientations of the Sagnac interferometer, the one with the axis parallel to the North Pole being the one that will experience the most rotation, and the one with the axis perpendicular, the one that will experience no rotation. We choose these two because we're going to flip between each orientation so that we can see the maximum change in fringe shift from one orientation to the other. These are just some pictures showing the Sagnac interferometer in some actual orientations. This first one is with the z-axis parallel to the North Pole, so it should show the maximum rotation. The second one is showing the z-axis towards the South Pole, and this should be perpendicular to the pole, so it should show minimal rotation. The next two are for our negative controls. They face with the z-axis either west or face east, And these will show partial rotations, which will cancel out. So flipping from one orientation to the other should lead to a zero result. So the way that we collected the data from this experiment is as follows. The interferometer sits perfectly stationary in a particular orientation, in this case first in the south orientation, and we collect a baseline signal for about 5 to 10 seconds. Then we manually flip the interferometer over to the perpendicular direction and then take another baseline reading. So we've got essentially a baseline, and then some noise from the flipping of the instrument, and then another baseline. And this is how we compare the amount of fringe shift which has occurred from one orientation to the other. We can then use the millivolt difference between each orientation and our calibration data to determine the rate of rotation the device is experiencing due to the Earth alone. The negative control progresses pretty much the same way. We start with our baseline on the east-facing configuration, and this is just showing the east-facing configuration here. We then flip it over to the west-facing configuration and do a second baseline for 5 to 10 seconds. And we repeat this process over and over again, flipping from one orientation to another, but keeping it stationary while it's doing the baseline. And then we find out what the average millivolt change is from one orientation to another by doing about 20 to 50 readings. This is just the details of our calibration. We did calibrations for the first and second experiments, the first experiment being 50 readings, the second experiment being 20 readings. And we have the experimental results shown in the table on the lower half of the slide. Essentially, we were expecting a difference of around 19.44 millivolts in the first experiment for our full rotation, and we got 21.76. And for the second experiment, we were expecting about 65 millivolts, and we got 57.5. So we're pretty close to the expected values. And for negative controls, we were expecting around 0 for each set of readings, and we got 3.1 millivolts in the first and 2.5 millivolts in the second. So I think this was fairly accurate for this first pass experiment with this instrument. What have we demonstrated with this experiment? First, we find that the speed of light is slower counterclockwise and faster clockwise around the loop, leading to our measured fringe shift, even though the interferometer is stationary from our perspective in the lab. Because we are detecting Earth's rotation, it means that the speed of light is constant in some other preferred frame, this frame being the Earth-centered inertial frame. Someone sitting on the North Pole would be in this frame. What this means is that for all other observers on the Earth, the speed of light is actually not constant at all. This implies that the constancy of the speed of light, which is a postulate of the theory of relativity, is very possibly an illusion.
Yeah, so awesome video.
Okay,
so
now I get it.
What's up?
No,
I just said, oh, now I get it.
Yeah, it's just an illusion, you know.
so I
I'd
don't
like
get
to
his.
get one of those. Oh, sorry.
Yeah, same.
No, you're good. I was just saying, I don't get his orientation. I don't get his choice. Like, he believes he's on a ball, right?
Yep.
So what? Why did he set up his axis like that? And if he did, right, and he was supposedly expecting some type of rotation, I wonder how that would affect trying to measure the ether drift. If the rotation that is being measured is the ether drift, then would it affect the laser interferometer or whatever by having it at a 45-degree angle rather than perpendicular to the ground?
It takes readings either way. To get the strongest reading, you have to have it axially aligned with the sky, or on the globe, they say you axially align it with the axis of rotation, and they do that by aligning it with Polaris. So in the northern hemisphere, on a globe or a plane, to get if it's a vortex emanating from the North Pole, you would do the same z-axis correction to get the maximum fringe reading.
Only to the north.
It's where the source is.
Right. That's so wild. Even I don't get that. So why did he expect a null in the negative? I don't
Because
get how.
C should be constant.
When he
No.
wasn't when he was doing east-west readings.
The south axis or whatever. His
Wait, the south was null?
It was like almost null. Yeah. That's what you were saying in the video.
I thought he inverted it and got 7.5 as well.
Yeah, I saw
and
a fringe. Yeah.
3
yeah, and then he adds them, and then he adds them together, and then it's 15 degrees per hour, if I'm not mistaken. I don't know, I have to come
Oh,
back
I
to
know
it.
I know what you're saying. I know what you're saying now. I get it.
Got it figured out.
Yeah.
Cool. All right, cool. So yeah, so that's what they say. That's how they say it works. This is their go-to proof. This is a go-to proof for single-axis gyro readings. Now, for single-axis gyro readings, real quick, let me just touch on that. Quick, let me make sure I'm sharing the right screen. So for single-axis gyro readings, there's 2 observation stations in the north. One is in Pisa, Italy, and the other one is in Germany. So they're both around the 45th latitude, and they both note that their correction angles are 45 degrees ish. So there's no distinction here on a globe or a plane or anything or whatever. Oh shoot, closed out the wrong one. Second. All right. Now, when we get into those single axis readings, again, if you assuming that the ether flow follows toroidal geometry, well, you would so the source of the motion is from the sky. You would actually make the same correction angles on a plane. As you get further away from the center axis of rotation, you would have to tilt tilt the device's z-axis to maintain alignment to get the best readings. So that's what that would look like. This was modeled out by Icon Science that made a nice model for us. He's not a glober. I mean, he's not a flat earther or anything like that. So this is just something cool he made for us. And then to kind of depict what that looks like here. So when they say, oh, we took this reading and it's the cosine to the latitude, therefore it has to be Earth rotation, et cetera, same exact concept. The sky's moving 15 degrees per hour. The ether flow is doing the same. It's gonna, as you get further away from that vortex, you're gonna have different fluctuations within that. So this is kind of what it would look like with a vortex emanating from the center. Oh, god dang it. 1 second. All right, so there would be the inner donut and the outer donut. You would have your convergence and divergence of the field. At the equator, you would have a flip zone, which we'll get into in a little bit. But this is just like a rough outline of what it would look like. So again, emanating vortex from the North Pole, sun's doing its analemma, doing its thing as it's going around. Yeah. All right. Let's see.
Wouldn't that imply that the reason you can't see like half the stars during half the year is because they're inside the ground underneath us on the projection?
Wouldn't that imply that half of the stars are in the ground on the projection?
Yeah, on the outer donut.
The
outer donut as it's counter rotating. The outer donut as it's counter rotating, it's still a full circle projection, right? So it's projecting the band over a full circle, which is the full field of stars. Half of it's on the outside, and you can see it. They say the other half is due to like your motion further north or south, but like the projection is like inverted on the plane. So like they would actually be in the ground. That's why you can't see them. And as you travel north or south, like the whole circle like inverts and turns.
No, I have no idea what now. I don't know what you're talking about. So
toroidal geometry. Sorry, go ahead.
Yeah, why have a uniformly rotating platform? Why they have to deny a uniformly rotating platform with the Sagnac effect, right? Because it actually is going to turn out that this is detrimental to everything, right? So let's see. So this is from Hasselblad, 1993. They do a summary of different quote unquote solutions for the Sagnac effect. They cite 23 different solutions in one general relativity solution provided by Paul Lavoux. Now, it should be noted that all these solutions are basically just different ways to geometrically look at the speed of light. Basically, it's a way for them to acknowledge the speed of light is varying while trying to maintain their belief system. And it's usually what they'll do is they'll invoke a transformation, watch the event from a geometrically convenient position, and then deny that the uniformly rotating platform is an inertial frame. Because then the reason they have to do that is because they have to take it to this general relativity explanation that was provided by Paul Lavoux, because all 22 of these are all insufficient to explain the actual fringe shift pattern, and because they all do things like invoking absolute space to preserve the distance, or they invoke an imaginary velocity vector for electromagnetic propagation to preserve the time, right? To make everything appear proportional. And then if you do that, then you can't explain a physical fringe difference, right? So none of these actually explain anything, and it's just kind of a bunch of attempts to flailing in the wind or whatever, as they say. So shout out to Hasselblad for making these all convenient in one location. So a lot of these involve things like, okay, so we're in the lab frame, we do our experiment, but the speed of light changes. So how do we get around that? Well, if we transform to the North Pole and we watch the lab frame, we would see that the speed of light is the same. Like, they literally do stuff like that to try and invoke that the speed of light is the same, but you just have to transform, that kind of stuff. So, and they will get into the general relativity explanation that they give, and this is ultimately the reason why they have to deny that a uniformly rotating platform is an inertial frame. Is the explanation, because general relativity is the only one that will allow them to even attempt to provide a mechanism to explain the physical fringe. So let's see, deny the validity of the frame of the closed uniformly polygonal. So I kind of went over that. All right, so now we're going to get into the mainstream explanations that they give, and which we kind of already did, and then we'll touch on Paul Levu, who came to the rescue. So this is from Tartaglia. This is a paper this is like the best kind of what would you call it? Like the best steelman of the mainstream position regarding the Sagnac effect and relativity. So he says here at the beginning of his paper, he prefaces, the Sagnac effect may easily be described in classical terms if one assumes that the speed of light is c with respect to a static ether. Considering a rotating platform mentioned in the introduction, you will see that it will take longer for the light to reach the emission point of the rim just before the platform. Meanwhile, because the receiver has moved by a forward vistic, right? So how are they going to get length contraction and time dilation out of this? Well, they can't. So they turn to your boy Tartaglia to invoke a geometrically convenient frame where they invoke absolute space as before, and then they use this transformation. They use a Lorentz transformation to basically watch the event unfold from a inertial frame, and they deny that the uniformly rotating platform is an inertial frame. So you're probably wondering, well, Alan, that doesn't explain anything. Indeed. As noted by Tartaglia himself, he says at some point in there, or was it, that this was like a thought experiment that they were doing to show this. This isn't even anything that they can quantify. This is just their explanation, and then obviously it's subpar, right? So there's another
also real quick too. That's right back to they're violating page 1 of the 1905 Einstein paper. Like, that's explicitly what they're doing right there, is assigning the velocity vector. But yeah, sorry, continue.
No, that's super important. Thank you for pointing that out, because like, if anytime you forget that, like, that's how they get you. Because they use that to weasel in the Lorentz transformation, but it's all predicated on preserving that space to assume, or it's all predicated on assuming absolute space and time to preserve the distances traveled or propagated through, so that they could maintain C on the other end of the transformation. So Einstein's whole thing is, we don't need it, but it's literally based off of.
Yeah, it turns out when C is not constant, and you're like, oh, well, we need to actually like have some kind of at least some kind of math so we can explain this. It's like you can't even make an equation to like post diction, like, or ad hoc explain it after the fact. You have to invoke an absolute time and an absolute space in order to even do the equations. Like, it's just, you can't do it any other way. So the whole thing is that incoherent from the get-go.
Dude, it's that bad. And then so another explanation was given more recently than the Tartaglia one, because this is an older one, Tartaglia. So this guy took a crack at it. Forget his name. It was 1 second. It was Barada. I'm not going to attempt to pronounce that, but shout out to those guys. They gave their solid attempt. But anyway, they do the same thing, and they say, well, this is a thought experiment, and explaining the fringes is really hard without any sort of transformation, right? So That's the take on it. They have no relative. They have special relativity has no answer for this. They have no way to explain the physical fringe pattern on the other end of that measurement. Man, they got like even at the highest levels of academia to this day that they've published, it says they got nothing. So continue on here. So this is Paul Lavaux. So Sagnac was in 1913. And then until 1917, it took a couple of relativists to come up with a derivation to answer the fringe. But again, it's not an actual answer. So Paul Lavaux had to step in and invoke general relativity and say, well, lads, because it's rotating uniformly, we'll just go ahead and treat that as an acceleration. And because it's an acceleration, we can now use the equivalence principle to say that this acceleration is equivalent to generating a gravitational field that will give us little temporal pockets of time dilation and length contraction. And using conservation laws, using the conservation metrics through through general relativity, they were able to conserve momentum on the small scale of a local rotating interferometer, like at non-relativistic speeds. They were able to turn that into a gravitational field to produce length contraction and time dilation to actually explain the fringe. So now they have a mechanism, right? Well, I mean, like obviously they don't have a mechanism, but they have a pretend mechanism of length contraction and time dilation to actually explain the fringes, right? So now we'll continue on a little bit and we'll come back to old Lavaux here in a minute. So we have Michelson, Gale, Pearson. Oh no, it covered up my other slide. 1 second. All right, we have Michelson, Gale, Pearson here. Let's see, move to front. Okay. So what they did here, Michelson, Gale, Pearson, they had pipes that were about 1 kilometer long, making a rectangle. So if you kind of look at the globe, right, it would look like that. Where on a plane, it would be, just flat. And then, so the aim here was to show that the speed, or to measure the quote unquote rotation of the Earth, right? To show that the speed of light is, the end result of this experiment shows that the speed of light is different traveling west to east than it is east to west, and there's no variance in the north-south propagation here. All right, so to get into the paper here, what they say is this is from the abstract here. This is Michelson, Gale, Pearson, 1925. This is the theory of the effect of the rotation of the Earth of the velocity of light is derived by the hypothesis of a fixed ether. So they got their variables here. So they got their north-south pipes, the ones facing north-south, and then they got their east-west pipes, and the variance is shown in the east-west pipes. And so, and another thing that they say here in their paper is that they calculated the displacement on the assumption of a stationary ether as well in accordance with relativity theory. So remember the invoking absolute space to preserve the distance of rotation. So what they're doing here is they're saying that, well, let's start with this bottom corner here. Let's say that the signal is sent from right here. It goes here, hits this, right? This is our travel up, or our length of travel, right? So it's going to start here, and it's not going to hit here because the Earth's rotating. So it has to move an extra distance. So now we're assigning additional velocity vectors for electromagnetic propagation and invoking absolute space to preserve the total distance traveled so that we could have this rotation, right? Now, if that's also happening, similar to, Coriolis and all that, distance traveled not being the same displacement, well, this is traveling north to south as the Earth is rotating. So this can't be in the same spot either, right? This has to also change, but it doesn't. There's no variance north-south. Even in GPS, when they've done signals where they relay to stations that are at the quote-unquote North Pole, there's no Sagnac corrections needed for that propagation when it's north-south. So the idea that this is due to Earth rotation is gone right there, essentially. And also the explanation provided, like just saying this in the paper, oh, it's in accordance with relativity, and they don't show any relativistic derivations at all. They just go with the ether, which invokes absolute space and time to explain it. Let's see. So now we move on to 1942 with Dufour and Pruner, who redid the classic Sagnac experiments with the classic configuration. where the light source and the photographic recorder are on the rotating device. Now, to make something clear real quick, what determines the state of an inertial, or like is a frame inertial or not, is determined by where the observer is. So if the observer is on the rotating platform, and that's where the measurement's being taken, that's where the photographic plate is, that's the observer. So you would consider that frame being taken in an inertial frame, right? If you were going to follow Einstein's doctrine about a uniformly rotating device or whatever, right? So they did the original Sagnac configuration just to see if that held true, and it did. They got a fringe pattern that corresponded to the rotation of the device and the length, or the total length of the total path of light, the total length that light had to travel, right? So they did another configuration to test another variable. This one was where the light source was off of the platform, and then the recorder was still on. Using collimators, they reflected the beam and made it all nice and crisp so they could get their measurements. And the measurement there was in accordance with relativity theory, where the speed of light is independent of the light source, right? So everything was good there. And then they did a third configuration where the light source and the recorder are fixed to the lab wall, and there's also a recorder fixed to the rotating device. And there'll be a beam splitter that'll hit that photographic recorder, and one that goes back to the photographic recorder on the wall. So in this configuration,
wait, so obviously the one on the wall had a totally different reading, right? Because it's not in the same inertial frame, and we all know that it's based on the being in the same inertial frame in that loop, right?
No, turns out they had the same reading.
Alan, you're making things up. What kind of pseudoscience paper is this? Come on, they didn't actually do this.
Dude, they not only did they did it, they had Paul Lavue step in to try and explain it. So he gave the relativistic derivation for an observer. So let me back up a second for the mechanism for how Lavue explains this, or for how they all explain it, really. So the baseline thing you do when you're analyzing this, it doesn't matter where the photographic recorder is. During the transformation, the process is to center yourself with the axis of rotation so you could be symmetrical and observe it from that location outwards. So you have to choose this frame at the center here, where and this frame can be considered stationary, right? Even though it's rotating, it's at the center, it could be stationary or rotating. So they take that frame, they take this preferred frame, and then they could make their relativistic derivations for things, right? And again, not even explaining the physical of the fringe, but just to even pretend, they have to use a preferred frame at the center of the device, right? So in Paul Lavue's metric and general relativity, they do the same thing with their transformation. They're at the center of the device, and then they invoke their length contraction and time dilation relative to that preferred, or relative to that frame in the center, which they say that they're just choosing for mathematical convenience. It just makes the math a little shorter.
I think you're wrong. I think it's just covariant, and they don't have to do any of that.
Yeah. I wish, or they wish, I guess.
Sorry to interrupt.
You're good. You're good. So Paul now, he's like, no worries, boys, I got you. We'll figure out everything based off of where the observer is located on the wall and that total distance traveled and all that. And it turns out that relativity could not make the prediction. So the classic theory predicted the amount of fringes that was measured, and the relativity was off by an order of magnitude, off by 100, I think it was. Was it off by? It says it here somewhere.
That's a factor of 10. You can see it in the figure, dude.
Oh, right here, factor of 10. Thank you, sir. So it was off by a factor of 10. Couldn't answer the fringe shift pattern from its location. And then Paul's like, well, because it's a uniformly rotating device, you have to assume gravitational effects are involved, and we have to use the center of the frame, and use relativity how it's intended to be, or whatever, right? So that was his hand wave dismissal of the situation, even though there's not supposed to be a preferred frame, right? All inertial frames are created equally, or whatever, right? So then we move on to 2004 with Ruyang Wang, who did a landmark experiment in interferometry with a a fiber optic gyro. In this particular configuration he did here, where these two bits here that wiggle, they cancel each other out. This remains stationary. and this back and forth linear motion is measured. Now we'll get into. We've heard lots of explanations to this, that it's measuring relative motion to the detector, that it's measuring relative motion to the other parts of the closed loop, that to like the total coil, XYZ. We've even heard invoking absolute space and time to preserve the total distance traveled in assigned velocity vectors for the propagation and all that. So there's no answer to that, and this should not be detected. So this is a linear motion detection. So the Sagnac detection with special relativity, they say, oh, it's a rotating platform, can't detect it, it's acceleration, blah blah blah. They hand wave dismiss it from relativity, and they pass it off to the homie general relativity to explain it. So in this situation here, where they're detecting linear motion in this configuration, this is actually a direct violation of special relativity, and the only explanation for that is to defer back to Tartaglia and what was that other guy's name? Bahadra. Bahadra. Yeah, you have to defer back to those guys and do Lorentz pretends and just transform. So let's say maybe there is some loop configuration, and maybe it is a loop and it just can't be measured, and it is whatever, right? So let's move on to a phase conjugate mirror and see what happens there. So in a phase conjugate, or in a conventional mirror, when they're sending these wavelengths down these paths, right, to complete these circuits, and it bounces back to complete its loop, it reorientates the wavefront. Now in a phase conjugate mirror, it basically it preserves the orientation of the wavefront and sends it back, so it kind of looks like it's traveling backwards in time. You can see the wavefront. So with this configuration here, using interferometers where you split the beam, you cancel out the one beam because you don't care about that reading. You just take a one-way reading on one of the arms of the interferometer using a phase conjugate mirror. And what they found in a rotating one is that the speed of light is already changed in the one-way direction. So a lot of there's some speculation on the speed of light, like is it the same two-way, is it one way, blah blah blah, right? Like when does it change for the for a fringe shift pattern to register? Is it when it hits the mirror, is it on the way? Who knows, right? Well, it turns out using a phase conjugate mirror, they found that it happens en route, one way.
I mean, don't they literally kind of imply that the light knew you were going to look at it or something? Like that's literally where they go with this, right?
No, this isn't in relation to.
Well, I guess you're right. This is not the same duality. You're right. This is just, wow.
Yeah.
This is just another big old hole.
Yep. And then we move on to Bilger in 1993 with the ring laser precision measurement of non-reciprocal phenomenon. So if we recall back to the configuration of the Michelson-Gale, this is the same situation, except this one was done in, I think, Christchurch or Australia, and then there's a new one that's in New Zealand as well. But this is 1993. They made a more precise, more sensitive Michelson-Gale apparatus, and using this configuration, they received quote-unquote fringe patterns that correspond to Earth's rotation in the south. And there's not a lot available on this for the data to analyze or whatever. But apparently, A.G. Kelly did some analysis on this and has stated several times that through his analysis of it, he determined that the speed of light, that the preferred direction that was shown in Michelson-Gale Pearson, where it's faster east to west, actually flips in the south, and it's faster going south to east, which is a complete falsification of relativity theory on itself. It falsifies the reading being due to Earth rotation, because there can't be a flip in the preferred direction of electromagnetic propagation due to Earth rotation. The Earth rotates in one direction. It would have to follow suit in all latitudes. It's not like a Coriolis thing where it's like, oh, well, now it drifts, differently or whatever. That's not how that works. It wouldn't work that way. So the explanation that they give is basically not really talking about this. Like I don't really ever see anyone bring this up or mention it. Like the only one that they talk about is the one in the north, because they don't have to address anything weird, because they don't even get into the analysis of the variance, right? Of like which pipes, which directions produce the fringe going faster or slower, right? they just get into oh, there's a fringe corresponds to Earth rotation, right?
Well, you gotta hand it to them. That's a wonderfully obfuscational kind of term, non-reciprocal phenomena. I mean, anybody who's actually researching the topic is going to look for things like asymmetrical interferometric data on the opposite hemisphere. All of that, none of that's in this fucking title. I mean, bravo, guys. Way to go.
That was our
It's so
read, too.
funny. It's so funny you mentioned that because that's exactly the kind of verbiage I was searching for. And there's just nothing, dude.
The words I use, I called this paper obtuse. Like, it just seems to be purposefully abstract about a lot of the ways it phrases things. And,
and then,
one other quick thing, Alan, you mentioned New Zealand, like as if there's another interferometer in New Zealand, but like, let's clarify, there is no interferometer they're taking readings from in New Zealand. New Zealand.
There is.
What's that?
No, there is. They take their readings and then they compare them to Germany and then they throw out whatever's wrong and then they go, look, we match Germany.
Oh, I thought they were like basically taking Germany's data. Okay.
No. It's a collaboration, and by collaboration, they're forcing symmetry relative to the latitude.
Okay, I'm gonna have to look into that more later. That's interesting.
Yeah.
I'm going to offer testimony as a local. I will say now, anybody present at either Christchurch or Dunedin at a POSAC Institute are far too busy burning couches in the street drunk as fuck instead of doing an experiment such as how you paint here.
Hell yeah. They're not. So what you're telling me is they're not looking for the non-reciprocal phenomenon out there?
They're not looking for anything. They're looking for their next brew. Okay, they're looking for things that are flammable.
Nice. Another interesting thing to note about this experiment. So how Doug was saying in the north for the single axis gyro, you have to have it orientated a specific orientation to get those readings. So in the north here, we got that 45 degree. So we should, and then I'm not going to pull it back up, but going back to those two observations, or laboratories in Italy and Germany, those have their 45 degrees. So what are the odds that there's a 45 degree correction in the south? Or some degree of correction, right? Just any, right? Turns out they mentioned that they keep it perfectly level. So the interpretation of that on their end for the globe would be parallel to the local horizontal, but it's like, obviously it's literally just level. And they somehow got a reading that matches the 15 degrees per hour or whatever out of that. So just an interesting tidbit to note there on the alleged, needing it to be in a certain orientation to be proof of the globe. Okay, so now we're going to get into some relativistic kind of counter arguments to the Sagnac effect, to these measurements, right? To the variance and the speed of light. So as we kind of went over earlier, the distance change in a platform, the time on the rotating platform is different than the lab, right? So these are Kelly's responses to those in a paper that he wrote, kind of did like a back and forth Q&A. I thought these would be useful. So another defense of the relativity theory is that the light path upon the disk is longer in one direction than the other, but the circumference upon the disk, as measured by someone upon it, is surely the same in both directions. So they're always trying to like change the radius of it or change the length, the area, all this stuff, the length contraction, blah, blah, blah. Oh, it traveled, distance is different through absolute space, etc. But this equation here doesn't mention anything about a changing of area, right? It's a fixed area, the total path traveled. This angular rotation here is just how fast it's spinning. 4 is just the distribution of that, of the rotation rate and the area traveled over c squared. So there's no like, hey, and then like there's no variable here to say, oh, but the time in the lab frame will be different from blah blah. Like, no, this is just straight up a proportional velocity relationship derived from the angular rotation of a device and the enclosed light path or total path of travel. Sorry.
Okay, but does anybody ever take the time to plug the numbers into reality, into these formulae that they loft out like fodder? Anybody actually take a look? It's always this c squared thing that is, I find, so numerically and arithmetically damning to anything that they're saying. And I'm going to digress on this, or actually, I guess, I'm going to circle back on what you were talking about before in regard to falsifiability. But by all means, Alan, continue right where you're at.
Yeah, no, thank you. So in regards to maybe the time is different on the platform, right? So the formula can be derived by assuming that light travels by relation to the fixed laboratory, but the measurement of the time difference is due solely aboard the disk. What can this mean? The only explanation possible is that the time aboard the spinning disk is and the fixed laboratory is the very same. This is not in accordance with special relativity theory. So if these two, like, this is why it's so detrimental to them to like avoid this as a special relativistic effect and pass it off to general relativity, because they can't even touch this without denying that it's that the frame is inertial and it's in special relativity applies. So I was going to read some more refutations from Bennett's paper and then close out on that. Do you guys so Stone, if you want to touch back on the C squared thing real quick, and then we'll just read off some. Stone. I'm not sure if he.
Yeah, maybe.
Here, now you should be able to hear me.
Oh, cool.
Oh, there you go.
Okay, yeah, I was just taking the bind off because I'm over to a spreadsheet and punching Q is really messing things up.
Oh, you're good.
Okay, so here we are. Like when you look at that figure, the 1/2 t squared over c squared, just plug things in. You're going to take your one clock, and let's say you're going to go for 1,000 seconds in one direction. Okay, that's like 16 minutes. And let's say you're going to go 1,000 meters per second while you're doing that. That's like Mach 1.5. So you're moving, and you go in a net of 1,000,000 meters there over 1,000 seconds, right? Well, what's the figure going to end up to be? What's t over there? What is delta t? It's 5.56 times 10 to the negative 12 seconds. Okay, we're talking billionths of a second difference. Taking this thing at Mach 0.5, Mach 1.5 for 16 minutes in some other direction, and the time between them is something you can't fucking measure.
Bro, that's
You know what I'm saying?
I'm so glad you brought that up, man, because they will try and invoke time dilation for like the pound Repka experiment, for example. And I actually found a guy who did the math on it, like how you just pointed out, and trying to give them like the absolute most benefit of the doubt, to basically like, make the math easier and just give it a nice clean reading or whatever. He ends up calculating that the time dilation, that if there was a time dilation effect in that experiment, it would be like 10 to the minus 21, and the experiment's like threshold measurement range or whatever, like it can only measure 10 to the minus 15. So it, like, the explanation given wouldn't even be perceivable, but people will just say it.
Even 10 to the minus 15 is not measurable with our current technology to any degree of certainty. They love that fucking word. You know what I'm saying? It's
Yeah.
it's ridiculous to consider those orders of magnitude at the same time. You're countering against their assertion that light's moving at 300 million meters per second, and all of these things are in meters and seconds. You know what I mean? And you're squaring that in the denominator. Like, get real, guys. Come on, that's 300 million times 300 million, and as a divisor. What are you saying about anything using figures that astronomically large and small? You know what I mean? Anyways, that's my rant about that.
Yeah, it's just it's where they get these like really tiny calculations, and then when they actually account for something, they're like, oh look, relativity's true.
It's just that none of it
He
is
said, understand
falsifiable.
that's
It's
20
all
orders of
unicorn
magnitude.
Exactly. It's unicorn fart fantasy land. You know what I mean? Pardon my food.
Yeah,
Yeah.
well, by the stats he gave first, it's more probable it's error.
Yeah. And then, all right, so we'll close out on reading some arguments on that Bennett provided that relativists will use to combat the Wang experiment. And it was actually, like, while reading through some of this one night, we actually went through like a whole gambit of these arguments with a relativist. So it was kind of refreshing to see, how they're misusing their own belief system to reify, to perpetually reify it and never have it falsified. So, contrarian opinions to the Wang fiber optic cable test. Claim 1. What explains the Wanging result is that light moves along a closed circuit and the observer is in motion with respect to that circuit. Reply. This is what the Wang test shows. 1. An object moving in the lab frame drags along the ether at the same speed. 2. Only the lab frame can be used to apply the laws of dynamics. Claim 2. The equation delta T equals 2VL over C squared is the base of the constant CC of the speed of light. Reply, the measured speed of light was C plus or minus V, not C. So yeah, we actually had this one. And it's like the only velocity component in there is the rotation, or in this case, the linear motion of the cable and the speed of light. So it's like, where's the velocity relationship coming from? Right? It can only come from one space. All right, so claim 3, the Wang experiment shows the results agree exactly with the predictions of special relativity. Reply, the principle, the constantly of the speed of light everywhere is the speed of light equals C. This is refuted by the result of the speed of light on the conveyor being C plus or minus V, where the speed V of the conveyor and the ether are entrained. So, like I was saying earlier, all motion will have its own ether optical vortex, as Sagnac called it. So that's what he's saying here. So the motion of the conveyor is also entraining an ether vortex with it. Claim 4. The reflected light will be red shifted from one mirror and blue shifted to the other, depending on the state of motion of the source of receiver relative to the optic fiber. Reply, there is no relative motion between the emitter and the receiver, and the fiber optic cable can measure the conveyor receiver and the fiber cable in the measured conveyor frame. Everything is at rest in that frame. Relative motion. See, that's what they were. I've heard that too. So, like, they'll say that, there's no relative motion there between there is no relative motion between the emitter receiver and the fiber cable in the measured conveyor frame. So the measured conveyor, yeah. Dude. Oh my God, man. Claim 5. The optical path links are different in the conveyor. This is my favorite. The optical path links are different in the conveyor, on the conveyor and in the lab frame. Reply, the speed of light is in both frames is equal to the phase shifts in time are equal to both optical paths traveled. So they're the same in both frames, right? So kind of like how Kelly was pointing out. Well, the time matches in the lab frame and it matches in the on the conveyor, or on the rotating platform. What does that? What do we make of this, guys? Claim 6. Dr. Wang linearly moved a straight section of the fiber while the rest of the device was held stationary. Reply, the source of the detector of the fiber optic cable was moved all together in the lab frame. The Sagnac detector, the fiber optic gyro reads C. When translating and non-rotating in the lab frame. When the interferometer is in linear motion in the lab frame, but only the linear segment produces a phase shift because the linear motion is through the ether. Claim 7. It has not been demonstrated that the linear motion of the entire device can register a signal. Reply, in fact, the graphical results is exact. Dude, I'm looking at that. Dude, that graph though. Let me look at that real quick. I just want to see that linear fucking graph real quick.
Yeah, isn't that great?
Oh, where is it? I need to see the graph. Yeah, right here.
Can you go back to 7 for just a second before you? Okay.
Nah, graph's already up.
Go ahead.
It's just your boy linear graph, measuring that linear motion. I don't know. That's funny. It's just nah. All right, what was your? Yeah. Yeah. Did you have something you wanted to ask, Piezo?
No, that's good, bro.
Okay. So claim 8, the phase occurs due to time and the velocity changes. Reply: the shift is constant at a constant speed, and the graph shows that's versus shows the graph versus the speed, or the shift versus the speed. The cause of the shift is the velocity, and not a velocity change equals acceleration. GG. Damn. How do I make that more red?
Yeah, it's getting pretty bright, ain't it?
Dude, god dang, like
This is about the point in the write-up where if Witsit was writing the replies, he'd be writing stuff like, "Oh no, man, now you're just panicking."
Dude, now you're just panicking, dude. Claim 9. We have proved that the Wang effect originates from the closure of two. Man, let me start that over. Claim 9. We have proved that the Wang effect originates from the closure of the two space paths, as seen in the frame co-moving with the emitter/receiver, and from the relative motion between the emitter/receiver and the optic fiber or physical device. Reply: in the co-moving frame, everything is at rest except the light beam and the surrounding laboratory. The beam path are always closed. There is no relative motion between the emitter/receiver and the optical fiber cable. Everything else is at rest. Why is this so difficult? Why is this concept so difficult? Why do you think it's so difficult, Tobe?
Is it because there's an Is it because
Yeah.
wasn't it because the cable's a closed loop, so you can't see anything from outside the cable's interfering with it, yet you have this like superfluous thing that's dragging through it and causing a shift in the light inside the cable that's on a closed loop. Yeah. Flowing through the cable, like like not through it like one point to the end other, but just like overall through the matter of the cable. So you have a micro refractive index change proportional to direction too. Would you?
Oh, dude. That's my favorite. We need to that 44% is deadly, dude. Because it's like, yeah, there's refraction, but also check out your boy still gaining a velocity and losing it at proportional. Like, dude, it's so
44%?
Yep,
That's a
going
huge
both
difference.
going both ways.
44% light and water, different direction, magnitude of velocity. Wow.
No, light, dude, it's just because the light's traveling through the particles and it has to, trek a longer path, but it's the same path, it's just different.
Yeah,
That's all.
It's not 44% in the open air.
Oh my god, yo, Toby, how about this, bro? You know how they say when a light goes through a window or whatever, it's still the same speed. It's just traveling a longer path because it has to bounce around and hit the molecular structure of the window or whatever. So, they're actually invoking absolute space to increase the distance traveled to maintain the speed so that they don't violate what's it called? Your boy energy conservation, I think it is.
I wonder what the proportionality is of a glass window. Man.
Well, it would have to be a moving glass window, right?
Yeah, right. But single pane or double?
Hell yeah, brother. All right. Let's see here. I think that's everything. So if there's no further questions, comments, concerns, or we'll probably end the recording there and then go into normal chat.
Great.
Shane, I hear you struggling with push to talk. That's awesome.
What the fuck is happening? My push to talk is also mic mute. So what the fuck am I doing?
Hell yeah, dude.
Yeah, sorry for coming in and just rolling through that, dude. Piezo, my bad, dude.
All right, well, I'm gonna go ahead and close out mine, and then we'll wrap it up. Oh, actually, before I end it though, Shane, I'm gonna need a Shane summary real quick off the cuff though to summarize everything we've been talking about for the last hour. Go ahead.
It's been missing for a while now. The Shane summaries.
Yeah, I might have been walking the dog. I might have fell a couple of times on the ice. I might have had my own adventure and not paid any attention. I'm sorry, dude.
No worries. All right, we're gonna.
Nice.
When in doubt, absolute space it out.
I love how you guys got challenged and then figured out some stuff and now added to the armament that we have of stuff to throw back at Globers, which is how it always goes.
Yep.
Cool. Well, I'm gonna stop my recording in my stream then, and I'll be back in a minute.
All right.
Cool. Sam, I'm gonna go to the bathroom real quick and